Yes. Okay. So let me introduce today's
Okay.
speaker. So welcome to the Series 8 Talk 3 of Countdown Seminar. So today we have Professor Ivan Arraut from University of St. Joseph, Macau. So he obtained his PhD from Osaka University, and he is interested in many topics. So today he will talk about something very interesting in cosmology. I personally say this is the problem of dark matter and dark energy. So over to Professor Arraut.
Okay, thank you very much for the introduction. It's a pleasure, it's an honor to be here and to give a talk to your institution. It's nice that you are doing physics there in Thailand. My understanding, only two universities right now are quite active in this field. My PhD, I am professor at University of St. Joseph, Macau, China. Whoever doesn't know, Macau is next to Hong Kong. It's called Las Vegas in Asia. We are full of casinos, full of many things. So it's a fancy place. Please visit when you have the time, if you have the interest to come to discuss or to give a seminar here. Also welcome. I am PhD from Osaka University in the high energy physics group. Actually, it's a theoretical high energy physics group under Yutaka Hosotani was my supervisor. And also, I had a second supervisor who was Hideo Kodama in the KK High Energy Accelerator. I am talking today, most of my research, either in quantum field theory or in gravity also, is focused on symmetries. In some cases, I have been looking for spontaneous symmetry weekend in some scenarios, but in gravity, I also explored some aspects in symmetry because the symmetries help us to understand and to analyze how the interactions behave, or in other way around, the symmetries govern the interactions. So let's start with an explanation because I will talk about dark matter and dark energy and how the symmetries can help us to solve these problems, symmetry arguments, I mean. So I have to start with the basic general relativity. We know when Einstein created this theory, founded this theory, is a geometric perspective. You have on the left-hand side the Einstein equations, which is the geometric part, and on the right-hand side the source terms, which is the energy momentum tensor. That corresponds to different components, density, momentum, etc., and pressure and so on. So the theory was successful. The successes of the general are numerous. It has not failed until now. And the most recent success is the detection of gravitational waves, which were detected, I think, around 2015, probably, by LIGO collaboration in the States. And they got the Nobel Prize in 2017. However, the evidence of gravitational waves was not new. We knew about that in 1974 when Holtz and Taylor they could predict that in a binary system, two objects, when they rotate around each other, they approach at a rate which is consistent with what general relativity predicted if the system emits gravitational waves. So it was an indirect detection by then, not direct. So that's why people didn't accept yet the existence of gravitational waves. They wanted to detect them directly. So the direct detection was in 2015, which is the one you knew. But before this success, of course, Einstein first confirmed that general relativity was in a good track, let's say, when he realized that his theory could predict the precession of the perihelion of Mercury. Basically, the planets, Newton said that the planets rotate in ellipses, which Einstein proved it to be wrong because in reality it's not an ellipse, it's, let's say, an ellipse which rotates in time because in reality the object, when it rotates, makes something like this, start to rotate, and this is called precession. This can be predicted by the geodesics when we calculate then through the metric solutions obtained from the Einstein equations. Another success of gravitation from the general relativity perspective is the gravitational lensing. Gravitational lensing is nothing else than the deviations of, of the rays of light due to a gravitational source. They said this was basically the second confirmation of Einstein theory. The first one was the precession of the perihelion. The second one was this gravitational lensing. I don't know if you know, but you should, if you read the history of general relativity, the famous eclipses experiments, which first was somebody, now I don't remember the name, but somebody detected, went to test the theory of general relativity. I think it was Eddington. Now it came to my mind. Eddington went to check with an eclipse
Yes.
that,
Yes.
yeah, Eddington in used an eclipse to test general relativity, and he realized that the theory was consistent with the observations. He could do some observations which were criticized by the time because people say that he manipulated the data in order to be favorable to Einstein. And that's why there was second excursions. Not only Eddington, but a numerous amount of scientists got involved in different points in the world for doing a second check of this observation, and they tested it, and general relativity succeeded. So after that, of course, Einstein became a celebrity because this appeared in the news everywhere, basically. Another effect of general relativity is the dragging effect. When an object rotates, uh, it's like having water. It's like the space-time is a fluid. When you rotate a fluid, imagine you rotate a fluid here, the water around will start to rotate. Well, the space-time is the same. If you put an object here, the rotation of the source will drag the objects around. This is more evident near black holes. For detecting, in my understanding, NASA put some experiment for around our planet or so to check, but they had to wait many years for detecting some appreciable effect. And it seems to be consistent with what Einstein was telling about. So even with the numerous successes of general relativity, still remains some problems in cosmology. As you know, cosmology has several issues, as well as other branches of physics. So we have two problems. One is dark matter, and I will explain why it's a problem. Because Newtonian theory basically predicts that the farther you are from the source, your velocity should be lower. In other words, let's put in this aspect. The moon, or let's say our planet rotates around the sun. If our planet is rotates so slow, it will fall into the sun. If our planet rotates too fast, it will escape. The same happened with the moon. No? So there is an equilibrium. Whenever you see objects rotating around each other, it means there is an equilibrium condition. And of course, for keeping that equilibrium condition, is you put the object farther away. Since the gravity is weaker, the object should rotate slower. But what these guys found is that in the galaxies, when you go far away, the velocity of the objects don't decrease, even when there is no matter around. There was no matter around for creating a gravitational effect, but still the objects continue rotating too fast for keeping the equilibrium. In other words, the galaxies rotate too fast for maintaining the equilibrium condition based on the calculations on the content of matter, baryonic matter they have. For this reason, many scientists they have to create a hypothetical matter called dark matter and put it artificially by hand in the galaxies and then for matching with the observations. The problem is that we have not detected any dark matter. It seems to be hypothetical matter which doesn't interact with anything except via gravitation. So, but the accelerators and so on have not been successful in the detection of dark matter. The other problem is dark energy. That energy is the opposite effect. It makes the things to separate, to split away. That energy means that the universe is expanding every day faster and faster, accelerated. The universe has an accelerated expansion every day. And it was detected in 1998, actually. The history is like this. When Einstein created the theory of general relativity, he believed wrongly that the universe was static. And the reason why he believed that is because when you see the sky with the naked eye, you don't see anything moving. No? And Newton also believed the same. But of course, something static would be very unstable. So the Einstein equations, when he developed them, suggested that the universe should be expanding. Then Einstein believed that was wrong, and he put a cosmological constant term in his equations. I think is the term which you saw here. This term here. This is the constant. He put with a negative sign, minus here. However, after observations done by Edwin Hubble, the same name of the telescope, the famous telescope, he realized that the universe was expanding, and he could realize that by observations of deviations to the infrared. When an object moves far away, the light, the wavelength elongates, and it looks more and more red. So this is how Hubble realized that the universe was expanding. And then everything was okay. Einstein, what he did was to delete this cosmological constant term. He said it was the worst mistake in his life, his career, or whatever. Then he deleted it. But then in 1998, the scientists realized that the universe was expanding faster and faster. Then the only way to reproduce that acceleration was putting again the cosmological constant, but with a positive sign. So the same constant which Einstein proposed many years ago is the same constant we propose now, but only with the opposite sign. But the problem is that the problem, of course, I will explain later, but later we will see that the problem is when we calculate the vacuum energy density, which is supposed to be the source of that energy or cosmological constant, and we obtain a tremendously high result in comparison with the experimental observations. And that's why it is called the problem of dark energy. Some people can call it vacuum energy, etc. Later we will revise this more. Then these are the two biggest problems in cosmology. Well, these are the Hubble tension, also the Hubble tension and the Hubble parameter measures in the past and the present differs if we use the known physics. And of course, inflation is another problem. The Big Bang, what happened during that period, all these kind of things are open problems in physics still. But this can be considered the two biggest problems. Dark matter represents about 30% of the content of the universe. I would say mostly at 27, 20 something. It helps the galaxies to keep stability even if they rotate too fast. That energy I interpret, and most of the people interpret as the vacuum energy, forcing the universe to expand in an accelerated form. As you know from quantum field theory, when you study the Klein-Gordon field, you will realize that since we use the algebra of the quantum harmonic oscillator for the quantization of quantum fields, you know perfectly that the ground state of a harmonic oscillator has energy. And the same happens with the quantum fields, and that's an infinite term which we remove from the equations in quantum field theory. But in gravity, this term is important because energy is a source of gravity, and that's what Einstein theory suggests. So let's talk about dark matter a little bit more. This is a simulation. I don't know if it works. Why it works. The left-hand side is the standard approach of Newton. The right-hand side is what is observed. So what we would expect by the observation of the galaxy rotation curves is this kind of rotation on the left-hand side. The farther you move, the slower you move. But instead, when you go far away, the velocity keeps constant, even if there is no enough matter for reproducing that effect. So this was the first evidence of dark matter. It was in 1933, and it became the famous dark matter problem. This is another way to represent the dark matter problem. This is the velocity. This is what you expect from the visible matter, but this is what is observed, more or less. Is the tendency to keep constant. Of course, it can increase a little bit, but with the distance, but this is also illogical. It should decrease. Remember, the farther you are away from the source is supposed to be here in the center, you should move slower. But instead, many objects, stars and so on, move at a constant velocity or a little bit larger. Let's put it this way: the Milky Way has the majority of the mass concentrated in the center. Let's assume we move a little bit away. We are rotating around the center, which has a supermassive black hole actually. The farther we are, we should move slower. But that's not what is happening. This is the first evidence. There are other evidence. Of course, gravitational lensing is another evidence of dark matter, which we will see later. Then dark matter, if we go to the Einstein equations, ignore the cosmological constant for the moment. If you go to the Einstein equations, this is the source term. Then what the majority of physicists do is to say that the Einstein equations are correct, and you input some matter here. Some matter with the hand, and you don't know what is it, so we call it dark matter. So this is the famous Navarro something profile of density. Some people create artificially profiles of matter density, dark matter, but they don't explain what is it. The real problem is to know what is dark matter. Another branch of a scientist, they modify gravity. They say Einstein is wrong and we don't have to put matter here, and instead we have to modify the left hand side, which is equivalent to modify the Einstein Hero action. And that's another issue because every time we modify the Einstein Hero action, there is a mess. I mean, the theories become quite complicated. And even if they can reproduce things, we have to input artificial felts, which we don't know what they are or so. So this is the other evidence of dark matter I was mentioned. You have a source. Einstein theory suggests that when the rays of light move around a source, they bend. No? So the more massive is the object here, the larger is the angle of deviation of these rays. However, if when precisely because of the presence of dark matter, this bend is larger than what is expected. Let's say we have visible matter here, we expect some bend, but the bending of light is much sharper than what we expect, and this is the second evidence of dark matter. The third evidence, of course, is the CMB itself, which is, and of course, the content of the universe, which requires dark matter and dark energy for being flat. The observation suggests that the universe is approximately flat when we develop the Friedman equations. And of course, the CMB, cosmic microwave background, also suggests that there should have been dark matter in the past, and in addition, for the formation of galaxies, because otherwise the universe, let's say, there had not been enough time for the galaxies to form or created these complex systems very stable as they are today if it's not for dark matter. So I mean, there are plenty of evidences that there is something missed, whether you modify gravity or whether some other things. So that's why it's a serious problem. For dark energy, the situation is different. Is different to dark matter. Dark energy is the majority of the content of the universe. 70% of the universe is dark energy, almost. And this is necessary for making the matching for the observations. That's why people believe it's vacuum energy, because there is nothing more abundant than the vacuum. When we see around, our universe is said to be vacuum dominated. Remember, the universe has different eras. The universe started with Big Bang. Then after, there was a period of inflation where the universe expand accelerated. And inflation is necessary for solving many other problems, which I will not mention in this talk, but they deserve to be seen also. Then, after the universe was radiation dominated, is where the CMB was formed. Actually, when the lights, the photons could escape from when the atoms were created stable, the photons could escape, but because before that the photons were trapped, and that's the CMB we see today. And then after the radiation domination, it gets matter dominated, which is where the galaxies and so on started to form. And then finally now is vacuum dominated, where the universe has started to accelerate, the accelerated expansion of the universe based on these Einstein equations here, with the cosmological constant now included. So, dark energy, one way to perceive dark energy, imagine, as I say, from quantum field theory, we know that the vacuum has energy, and there are plenty of evidences. We have Casimir effect, we have many other issues, many other tests which confirm that the vacuum energy. Otherwise, the accelerators, they would not be able to create particles from nothing. I mean, you collide two particles and you can create other particles, or some particles can disintegrate or disappear. And this is a consequence of the fact that our vacuum is very rich. It creates permanently and destroys pairs of particles. Electron, positron is created, subsequently destroyed. Proton, antiproton created, subsequently destroyed, and so on. Many, many particles in the vacuum, which we cannot see, we cannot perceive, but they have energy. And the problem is that when you calculate the vacuum energy density based on quantum field theory, which is a standard calculation, you obtain this result. The vacuum energy density is proportional to k to the 4. K is the momentum, well, it's related to the frequency, actually. It's the ultraviolet cutoff, which we take as the Planck length. No? This possible length in the universe is the Planck length. But it comes out that this result is 120 orders of magnitude larger than the experimental observation. And this is terrible. 120 orders of magnitude means 120 zeros to the right, not to the left, to the right. So it means if you have one, imagine that the observation gives you one, and you theoretically predict that it's not one, it's one to multiply by 10 to the 120. This is more or less what is happening. And this is the problem of dark energy from the perspective of vacuum energy. So the vacuum energy really exists. We have Casimir effect. We have many other consequences of having a vacuum very rich. Dark energy comes out fundamentally as a consequence of the algebra of the quantum harmonic oscillator. As you know, the ground state of the quantum harmonic oscillator has non-zero energy. Look at this spectrum of energy of the quantum harmonic oscillator. You have n0, 1, 2, 3. The vacuum is n0 when there is nothing. Still, the energy is 1/2 h bar omega. Omega is the frequency. Well, in quantum field theory, we have to zoom. We have to integrate over all the frequencies. And that's where you obtain the result which I showed you before, this one, precisely. Later on, I will talk a little bit more about this result. This is the algebra which we use for quantizing scalar quantum field. Actually, we have the quantum field, the canonical conjugate momentum. Is somehow the extension of the algebra we use in quantum mechanics, but extended to quantum operators. If you revise the book of Peskin or any other for the students, you will realize that this is the case. You have to impose an algebra, either this, or you have to impose the algebra over the creation and annihilation operator after expanding the quantum field in positive and negative frequencies. This is the representation of quantum field. You integrate over the momentum this way. This is the canonical conjugate momentum, and this is the Hamiltonian of the operator. What is the ground state here? The ground state is where this operator here is 0. This is the particle number operator, A daga A, which you see in ordinary quantum mechanics. So when this vanishes, there is still one term. This is the 1/2 h bar omega you saw before. Only that in quantum field theory is an infinity, and we in quantum field theory is not important because it's just an energy reference. Basically, you have one energy level. So you say, okay, I want to remove this infinity. I will set it to 0, and I will start to calculate from there. Nice, but in gravity we cannot do that. In gravity, we have to consider this term seriously because energy is source of gravity, and that's the issue. Well, what is the problem with that energy? How to decrease the 120 orders of magnitude coming from the 0 point quantum fluctuations, which is coming from the energy of the vacuum of from the algebra harmonic oscillator. The second proposal is to modify gravity. Personally, I work in modify gravity for some period, but after a while, I didn't do that anymore. I started to attach more to the standard theory to try to look for alternative solutions to these two problems. Then let's take a closer look to the problem with dark energy. Probably I will start talking first about how to solve the problem of dark energy, and finally I will explain how to solve the problem of dark matter from my perspective, at least. This is the integral we have to do in quantum field theory. Let's say this is the vacuum energy density. When you say the particle number operator to 0, you have to integrate all the frequency modes. This omega is proportional to k. Remember, this k here, k cubed. When you integrate, it gives you k to the 4 maximum, because it's the cutoff here. This 0 doesn't contribute. So, but this we learned before that this is the worst theoretical prediction in physics. So this is not the way. So what I have done recently is to analyze the theta solution. Then first I started with the static coordinates. It's a solution which looks a little bit strange initially, but after analyzing a little bit, it becomes clear. This is the theta solution. When we pose the cosmological constant in the Einstein equations, this is the solution for the spherical symmetry. I can make a change of coordinates because I want to translate the effects of the cosmological constant to the angle, which is what happened here. At large scale, this turn negligible, these two. So all the effects are here in this C. And then I want to analyze the symmetries of this metric. When you analyze the symmetries of this metric has two Killing vectors, one timeline Killing vector and one rotational Killing vector. So from the timeline Killing vector is just the standard energy. The rotational Killing vector gives you the conservation of the angular momentum, which is related, of course, when it's more or less this quantity here. This is the conserved quantity for the angle. Oh, there is an issue here. We can integrate this. We can integrate this angle. This is the azimuthal angle, and then we obtain a maximal angle. This has to be complemented. This solution here is in the space. How to say? You have to translate to the momentum this quantity. This is in position space. This is in momentum space. How do you do that? Via uncertainty principle. Okay. So I have to put beta r squared, integrate lambda, and integrate both sides. I obtain a maximal angle. And this is telling me that the larger the frequency of the mode coming from the vacuum, the smaller is the azimuthal angle cover. So it covers less space. So and the larger, is the wavelength, or smaller the frequency. Of course, the infrared modes, for example, they cover more angle. This is the azimuthal angle. Is different to the zenithal angle, which is theta. That angle is arbitrary, and I will explain what is the interpretation of this in a moment. So the integration, for me, the solution to that energy is as follows. Let's decompose the integration of the vacuum energy density in three integrals for theta, for phi, and for k. And this is the element of volume, k squared already multiplied over k, sine of theta, the k, the phi, the theta. If you integrate the first variable, theta, you obtain 2. So that theta defines the plane of creation of the pairs. I mean, when the vacuum creates the pairs, electron, positron, or any other, the plane at which they are created is arbitrary. So you have to sum all of them. The second integration is this azimuthal angle. It's related to the angular momentum. And this is the angle which is affected. It changes for each frequency mode in the way how I explained before. I obtained a publication about that result. Those who are interested, there is another result which is published in European Physical Journal C. I will show the reference in a moment. The point is that when you integrate this and you include this angle, maximal angle here, in the upper limit, this is calculus 3. Basically, if you study engineering or physics, when you include the upper limit in terms of the of k, obviously the k squared here will kill partially the k cube here. So of course it will decrease strongly the result. It will suppress. It's a strong suppression for the ultraviolet modes. Now I repeated the same calculation by using the Friedman-Lemaitre-Robertson-Walker. I use the homogeneity and isotropy of the universe, the de Sitter solution, which is nothing else than the same solution in static coordinates but in a different coordinate system, and I found this maximal angle, which looks weird because it has this exponential of h something, but take into account that h depends on time, so this result is not trivial. And for having the consistency between the two results, h has to change in time in a particular way, which I will show later, which is also consistent with the way how h should change in each era of the universe. But the point is that in the most general case, this is the result of the vacuum energy density. You have a strong suppression, so vanishing of this angle for the ultraviolet modes, and the infrared modes are the dominant ones. So at the end of the day, this has a physical interpretation. The physical interpretation is as follows. This is the result, actually. This is the formal result. And this is how it should give the experimental observation. And this is what we derive theoretical when we include the maximal angle. And the theoretical explanation, physical explanation is as follows. The pairs are created, electron, positron, or proton, antiproton, whatever. When the vacuum mode is near to the infrared modes are created by light particles which has a very small mass, very tiny mass. They can live longer. So when they are created, they are rotating around each other. If they have enough time to live, as is the case for the infrared case, they can rotate more and they can cover more angle, this angle. However, the ultraviolet modes, they are created by heavy particles. So it means they live less. They live less. So they don't have enough time to cover so much angle, so they don't cover so much phase space, so they cannot contribute so much to this integral. This is the interpretation of this result. And it was obtained in 2 publications. This is the one which I shared before. Initially, they didn't give me the issue or so, but now it's here. And this is the second publication which I obtained recently in 2025. So recently, I also developed a third paper about this where I proved the consistency between the dynamic approach and the static approach, because something which I didn't mention is that in this approach, R is fixed, because in the Friedman-Lemaitre-Robertson-Walker is a dynamical case. So it's the case where the galaxies are located in some points and they just expand with the background. It's different to the static case where R really, we care how R changes. So we take R here as fixed. We care is only the integration in time. This is the line that finished being the integration in time. And here we have to use the energy time uncertainty principle in order to convert this expression into the momentum in space. It's different to the static case where the uncertainty principle used here is the position momentum because we are in the static coordinates. So we have to use the position momentum uncertainty principle. But both cases match with, with the additional success that the Hubble parameter has to change in time as 1 over t, which is precisely what it happens when we calculate the Hubble parameter for radiation-dominated universe, even for curvature-dominated universe, and even for matter-dominated universe. You will obtain a Hubble parameter inverse of the time in all the areas of the universe. So this is demonstrated here, for example, in this result. This is the result of the maximum angle obtained via Friedman, Lemaitre, Robinson, Walker, with L is the angular momentum. This is the result obtained via static coordinates. Both of them match. Of course, we have to match some parameters, but still you can see that it's inverse of k squared, inverse of k squared here. So I think from my perspective, the solution of that energy will come from this perspective. How to prove this experimentally? Well, if there is an experiment suggesting that the ultraviolet modes cover less azimuthal angles than the infrared modes in the vacuum, that would be something. So it's something we have to think about. I'm discussing these things with some collaborators, some of my friends who are in the US somewhere, etc. So let's see how it goes. Now let's focus on dark matter. It's a completely different problem, but I wanted to talk about the dark universe for completing the square. I proposed a solution, a little bit polemic about dark matter in 2023. It was an editor choice paper. It received a common paper actually in 2024, but I replied to it. Subsequently, I published another paper about it, improving the solution in Modern Physics Letters. This one I have just received the issue number and so that's why it doesn't appear. And I submitted another paper recently actually about it, where I found really the final solution. So for me, the problem was in the symmetry assumptions at the galactic scales. I will explain what is that in a moment. For understanding this deeply, let's talk about the standard case. When we work at the solar system level, for example, we assume this solution. We have a metric answer. Actually, we don't know what is here. We don't know what is here. All what we know, the only answer we enter is the spherical symmetry, r squared the omega. Then we input this inside the Einstein equations, and after when we solve the Einstein equations for the vacuum solution, we obtain this result and this result. But this is an answer, this part. So this is a free answer. However, if you change this r squared to something else, the solution is not vacuum anymore. You can check yourself. That is not vacuum anymore. So from this solution, you can obtain the geodesic equations. These are the geodesic of this vacuum metric. Nice. Very complicated, right? Well, for time, radial, angles, and so on. Zenithal and azimuthal. However, you can have some symmetries. The symmetries simplify the everything. And the symmetries in the space-time are portrayed via Killing vectors. This is a timeline Killing vector, which is related to the symmetries under time translation, which becomes to be the energy. This is the energy conservation, actually. And this is the rotational Killing vector, which, as you can see, is related to the zenithal angle, and it comes out to be related to the angular momentum. Besides this quantity is also considered conserved, this epsilon. This is the line element, nothing else than the line element, and it's 1 for massless particles and 1 for massive particles, massive test particles, because what we do is to put a test particle around the source and see how it moves. And this is 0 for massless particles, for massless, like the light, for example. So without loss of generality, these guys fix the angle theta because the plane, as I explained before, the plane of rotation is arbitrary to pi half. When you do pi half, you kill the angle here. You put this to 1, and you don't care this the theta anymore. So just simplify all the geodesic equations are simplified to this equation. This is an equation in energy. Kinetic term, potential term, constant. And this constant is related to the energy of the system, which is called. These conserved quantities comes from the contraction of the one form. You have to calculate the one form of the Killing vectors, which comes out to be like this. After you have to decrease the download the index by using the metric. Those who study general relativity understand what I'm talking about. And then you contract with the variation of the variable in question. This is a conserved quantity. That's why this is the energy conservation, and this is the angular momentum conservation. And you input those quantities here, and that's it. Nice. And then you can derive by using the potential, the equilibrium conditions. You can plot the potential. This is for general relativity. This is for massless particles. This is for massive particles. What is the difference between general relativity and Newton? In Newton, we have this term, if epsilon is 1. We have this term, this is the centrifugal contribution, but we don't have this term in Newton. So this is the coupling between the source term and the angular momentum, and it generates an additional attractive effect, which in Newton doesn't appear. And this is the term, the guilty of the precessions and all these effects, additional effects. You can compare the Newtonian case with the general relativistic case. So this is a standard. So let's copy the techniques for solving the dark matter problem. One issue in general relativity is that people always assume spherical symmetry. So my point is that at galactic scales, there is no reason for us to assume that the symmetries are spherical. Then instead of that, I change the ANSACS metrics, and I will show you in a moment. But what I want to derive is the Tully-Fisher law, which is this. It's an experimental law suggesting that the velocity to the fore is proportional to the mass source based on baryonic matter only. And these are the scales of equilibrium for dark matter in agreement with modified Newtonian dynamics. But I will not apply modified Newtonian dynamics. I am just taking the results and I want to reproduce them here. This is the geometric average between gravitational radius and the inverse of the acceleration scale. One acceleration arbitrary, which in modified Newtonian dynamics appear, for example. And it comes out to be related to the cosmological constant scale for reasons which nobody understands yet. So I wanted to say that in my initial solution, which is not completely correct, it was not correct, but I will explain what was the idea. Initially, I changed it. I changed the spherical symmetry for another symmetry, and then I found this conserved quantity gamma squared, and you can see that there is a change in the way of the power for each, especially the centrifugal and this term scale. So I found some equilibrium conditions, etc. These solutions look beautiful. Initially, I could find some equilibrium condition consistent with Tully-Fisher law, but it didn't reproduce so much lensing actually. From my perspective, I didn't test the lensing fully, but it doesn't look like it will reproduce it. And another issue is that it was not a vacuum solution, because in the metric ANSACS, which is this is the metric ANSACS. In the metric ANSACS, I changed it here. Instead of put r squared, I put theta r, the omega squared. No, r squared theta is a parameter independent of r, which scale like the distance. But the mistake initially was that I took these two solutions as the spatial case. And it comes out that it's not a vacuum solution. Of course, it's a metric which deserves to be analyzed, etc., but it's not the vacuum. So recently, of course, after a while, thinking a little bit, I decided to find the vacuum solution, which is scale like this. And it came out that this is the metric. This is the real vacuum solution under this ANSACS on the angular component. You can see the t squared, and you can see that this component is not the inverse of this component. There is an additional term here. This is a vacuum solution. Of course, you can make coordinate transformations for making it look more beautiful, whatever. But every time we have a new vacuum solution in general relativity, we have to take it serious because general relativity has not failed until now. There is no known case of failure of general relativity until now, classically. Now, if you are talking about quantum gravity, which is, we don't know yet what is it. We have some clues with string theory, with quantum gravity, whatever you want to say, or some generalized uncertainty principles, etc. But nobody knows yet what is quantum gravity. Now, if we are going to the classical case, general relativity has no failed. Then if we find a new vacuum solution of general relativity, we have to take it serious. So the idea here was the same. I found just this equation, the standard equation, the time-like Killing vector, the angular Killing vector, and apply those conserved quantities to the equations of motion, and I found this potential. And when you find the equilibrium conditions of this potential, which are obtained by this, we obtain this scale, which is the scale which matches with the observations. It matches. And as a consequence of this scale, of course, you can obtain easily the Eur.Phys.J.C law. Again, the difference between this solution and the previous I obtained before, which was no vacuum, is that this is much more natural. So this is much more, how to say, you don't need to do any additional assumption or any additional answers, nothing. So this is the beauty part. So let's summarize a little bit what I did. You put this metric, you have to input because you don't know this function, this two, this and this. You have to input into the Einstein equations. The Einstein equations, let's find them. They are from here behind. You have to input here in the Einstein equations. Let's ignore the cosmological constant because at galactic level, the cosmological constant will not have so much. However, it's not something completely negligible because some observations, actually there are experiments where they measure while dark matter is trying to agglomerate matter, dark energy tries to pull it away. So, I mean, there are some scales at which we cannot ignore the cosmological constant. But for the purpose of illustration, that metric you saw before, I just input in these equations. This is zero and this is zero because it's vacuum. And then I try to derive, and you start to calculate what are the components which satisfy, or the functions which satisfy the metric ansatz. And by functions, I mean these ones. Let me show you. By functions, I mean this one. These two guys are the guys. And then you obtain this component and this component. This is more or less how you obtain the vacuum solutions. And any solution in general relativity. The spatial metric, the same. The difference between this and spatial, what is? Instead of theta, you put r squared. And again, you input that metric ansatz in the Einstein equations equals zero, and you realize that the only possible solution is that one, is the spatial metric. Now, the Kerr metric also is vacuum solution, but it's a rotational solution. It's a rotational solution. It's not spherically symmetric neither. That's axially symmetric. If you put charge, that's another issue. Charge as a source, then you have the radial nostril. But all of them are considered vacuum solutions in the sense that the right-hand side of the Einstein equations have to be set to zero. So obtaining this, and I will show you something else. This scale, these are the scale of dark matter. Why do we believe that? Because when we put the baryonic matter here of each galaxy, let's take each galaxy, and we put the matter, visible matter, the baryonic. And there's this R lambda like 10 to the 26 meter, which is the scale of the universe actually, because that's the inverse of the acceleration scale, which is a parameter obtained via modified Newtonian dynamics actually. But in this case, you will be surprised. Actually, I didn't write, but that acceleration is the inverse of this theta. So in other words, this A0 is 1 over theta. So that theta you see here is related to this square R lambda. When I input all the matters of different galaxies, let's call Messier 33, Milky Way, Andromeda, Antenna Systems, Cigar Galaxy, and you calculate that scale, which is this one here. You obtain the scale of 1.6 kiloparsecs for Messier 33, 4.8 kiloparsecs more or less for Milky Way. For Andromeda is around 3 or 4 kiloparsecs. For this is around 0.1 kiloparsecs, and so on. This order of magnitude, this is precisely the scales at which the dark matter effects appear for these masses. These are the visible masses of each of these galaxies. This scale, ignore it because it is something else I was analyzing. So the point is that we could obtain a vacuum solution able to reproduce, and I have to mention, the scales of dark matter, the Tully Fisher law, and in additionally the flatness, I didn't mention, but I have to mention, the flatness of the galaxy rotation curves. And now let's analyze the potential. Of course, C1 and C0 are arbitrary parameters. They don't affect this eta square is the conserved quantity for the rotational symmetry, is the replacement, is the angular momentum with respect to this metric. But remember, the angular momentum of this metric is not the angular momentum, it's the tangential velocity. Of course, r is the distance, and theta is this parameter which appear here. This potential can reproduce the galaxy rotation curves, the flatness of the galaxy rotation curves, and it looks like a promising solution able to generate the gravitational lensing observed, the observed gravitational lensing. So the next step in this kind of solutions is to test the gravitational lensing, which is what I mentioned around here. When I mean gravitational lensing is this. I want to test that the metric which we have proposed is able to predict the appropriate bending of the paths of light consistent with the observations as which are done under the assumption of dark matter. But the difference is that here I am not assuming dark matter. Here there is no dark matter. This metric solution was found without dark matter. So, in conclusion, from my perspective, it is possible to get dark matter effects without modifying gravity. You don't have to change the Einstein equations. All what you have to do is to modify the symmetries at galactic scales. Remember, symmetries govern the interactions, and this is not new. If you change the symmetries of certain interactions, they will behave different. Remember the Nobel Prize C. and Yang, who say symmetries govern the interaction. That's clear. That's in any, and then even in particle physics, in quantum field theory, everywhere is the same. For dark energy, we don't need to modify gravity neither. Well, let's put it this way. In gravity, in dark matter case, we don't have to modify gravity, but we don't need dark matter neither. For dark energy, we don't need to modify gravity neither. All what we need is to consider the symmetry constraints of the angular component. So it's the constraints coming from the angular momentum, which imposes a maximum angle for each frequency mode. In other ways, for respecting that symmetry, the spherical symmetry, each frequency mode of the vacuum has to respect some limits in the azimuthal angle, something which before, in my understanding, it was not obtained before. As I say, we don't need dark matter, and we don't need to modify gravity for reproduce the effects. We need to derive is a new vacuum solution. Now, how to solve the Hubble tension? That is the process, and it's related to what I portray here when I was talking about this part. It's related to the evolution of the Hubble parameter. Explain the Hubble tension. The Hubble tension is we measure the Hubble parameter now with the recession of the galaxies or recession of Cepheids or whatever, and then we compare with the observations in the past. But those observations are not direct. I mean, in the past, it means that you have to extrapolate them with the known physics to what is perceived today. And then you compare the results. And there is a serious mismatch independent of the observations, even with the James Webb telescope. This mismatch still persists between the Hubble parameter measured now and the Hubble parameter taken from the past and extrapolated to the present with no physics. So some people are trying to find new physics from there, etc. I think the consistency between the Friedman-Lemaitre-Robertson work and the static solution is also a key point to understand the time evolution of the Hubble parameter, which could be related to the Hubble tensions. And the final conclusion is, is what I just said. The Hubble parameter changes in time in a consistent way, such that the vacuum energy density today is very low. So, in other words, the Friedman-Lemaitre-Robertson Walker, when they is out another metric ansatz, we input in the Einstein equations, we put equal to the cosmological constant times G mu nu. When we derive the solution, we obtain that exponential we just saw before, and that's the de Sitter solution from the perspective of the Friedman-Lemaitre-Robertson Walker, because there is a de Sitter solution from the perspective of the static coordinate, but they are the same solution. Let me close this part by putting the metric, this metric. This is the de Sitter solution by using the Friedman-Lemaitre-Robertson Walker approach, assuming the homogeneity and the isotope. Not something important here is that the cosmological constant effects are here, and they are directly operating over the angle. That's why I didn't have to do any coordinate transformation for putting the cosmological constant effects over the angle. So this is more natural solution than even the static one, because in the static one, I started like this and I wanted to translate these effects to the angular part. And this is what happened when I do this conversion. But still, of course, the results are consistent. And finally, I would like to conclude saying that you are welcome here to Macau. This is a YouTube channel which I have. Crochet is also an organization we are forming here in Macau. Hopefully, growing very soon. It's related to research, with the permission of our institution, obviously. And we are creating also the quantum research group here in Macau. We want to encourage Macau people to follow more science, to be more science focused, because this will help in the diversification of the economy, which is one of the plans of Beijing and the chief executive of Macau. So then we are, as an institution from the University of St. Joseph, we are cooperating in this direction. Then, thank you very much. This is my talk. If you have any questions, please let me know.
Thank you, Dr. Arraut, for the nice talk. So, I open it for questions. If anybody has any question, there are online people also. Anyone? Anybody here?
Maybe they are shy.
Yeah, some of them are students, so yeah, I expect them to be shy. So, but if not, then yeah. Okay, let me thank the speaker for the nice talk and for the nice exposition. So
Sure.
thanks again, and yeah, we can like so let me first stop the recording.
Sure.